Today's speaker is Balaji, and he's been working on various topics at NASA Langley since 2010, so it's been 15 years now. And he's been focusing on transition modeling recently for subsonic flows. So he's going to tell us about this overview of his research effort on transition modeling for subsonic flows. And this is an informal seminar, so please ask questions during the seminar.
Thanks, Hiro, for inviting me to give this talk, and for those online and here. This talk, I've kind of structured it like more like an overview. I will get into different topics of it, but not in any detailed sense, but enough material to kind of pivot to what we are doing and stuff like that. So stop me at any point to have any questions, either here and online also. So this project is typically, as far as is funded through the NASA Triple project. I'm working for AMA, so this is funded through the research effort here at NASA Langley. I would also like to acknowledge several of my NASA Langley, AMA, pre-NIA colleagues: Ethan Vogel, Lee, Joe Derlada, Milan Chaudhry, Michael Donello, Nathaniel Hildebrand, Pedro Paredes, and Vishal Srivatsava. I mean, they've all been helping in different pieces of this entire project. So this is how I've kind of structured my talk. So we'll get into the motivation and what is the state of the art in terms of transition prediction and modeling, and emphasize on two particular approaches which we are focusing within our group here. One is based on stability-based prediction, and then the second approach is through transport equations, more like RANS models. Under each of these topics, we look at some test cases, and through those test cases help identify what are the bottlenecks and how we are addressing them, and what step we are taking to mitigate those effects and improve that. And then finish it with some summary. So as part of CFD Vision 2030 study, they had made statements that transition modeling is the critical aspect for CFD throughout the foreseeable future, and it's important to be able to accurately predict viscous flows with Laminar-Turbulent boundary layer transition. This has impact on different aspects of flow physics. If you take hypersonics, it's going to largely affect the thermal heat load and drag performance, as well as stability and payload capacity. For subsonic transport type vehicles, it means more efficiency, reduction of drag, safety. And it also has applications in like micro aerial vehicles or turbo machinery. So as part of the NASA project, we have a large technical challenge. The technical challenge is to develop and validate fully automatic transition prediction capability for CFD, incorporating the necessary physics with quantified uncertainty, and we are working towards meeting that challenge. So, for those who know the word who have been in fluids, we all know what is transition. It's a big area. People have spent decades or maybe their entire life studying this, so I'm not going to get into the full details of what it is. But the things that affect transition are several aspects, such as free stream turbulence disturbances, the surface roughness of the test article or the flight article, pressure gradient, surface curvature, whether the wall is being heated or cooled, is there blowing and suction or suction, presence of separation bubbles, 2D, 3D nature of the flow, all of these influence transition. And it influences transition, but once transition happens, there are multiple pathways through which the entire scenario can unfold itself. And on the right, we have this classic Morocco's picture. Where I think he applied, he gave us the various pathways through which, these disturbances or parameters can influence the flow and eventually lead to turbulence breakdown and eventually to turbulence. So as part of this talk, mostly I'll be talking through the pathways A and some of E. The pathways B, C, and D are not of the focus in this talk. So pathway A is essentially what happens is more through, the standard TS mechanisms, more like linear disturbance growth and stuff like that. So we're going to assume some linear assumptions and not talk about the nonlinear effects as much. And then essentially more to do with modal disturbances and things like that. So you have like Tolman shifting waves under that, Gautler vortices, those kind of things. And typically the pathway A is for more relevant to subsonic flows with mild disturbances and things like that. There's also the pathway B, which is like a little bit of transient growth where you have non-modal disturbances influencing things. And then slowly, as you move to the right, the nonlinear part takes dominance. So you'll have to carefully understand the physics and put all of that into your modeling mechanism. And then there's also the E mechanism, which is like you completely skip over the linear growth part and then directly go on to the nonlinear behavior and then slightly go into bypass. So the bypass is more important for turbo machinery and application like that, where you have large turbulence disturbances in the field. So mostly we would like the approach we are taking, a lot of it would address pathways A and E. Path C and D on B is also important for hypersonics. And Pedro here, who's sitting in the audience, he focuses on some of the aspects of B and C, and D probably also a little bit. And I think, correct me wrong if I'm wrong, I think pathway C, where the transient growth and the C is also important for subsonic flows a little bit. You know, it's much more complicated. So in terms of the state of the art approach, and again, here I'm only trying to keep it to subsonic flows. There's an equivalent group at NASA Langley who's studying hypersonic transition. In terms of RAN-based modeling, there's Ethan Vogel who's looking at that, and then Pedro Paredes, Fei Li, and Milan Chaudhary are looking at more stability-based methods in that regards as well. And Vishal Srivatsava is like he's trying to build more like machine learning-based models of addressing the same component for both regimes. So on top, we have the classical wall-resolved LES or DMS. As we all know, this is extremely computationally expensive. But what makes it even more difficult for transitional flows, we should be able to characterize the inflow conditions. So the disturbance environment has to be completely characterized for it to actually, you know, to be able to, for the system to be able to model that, predict that, and boundary conditions. And a lot of times, the disturbance environment is not completely characterized even in experiments. So there's a huge gap there. So although this is like a nice approach to pursue, but it's like not yet feasible and it's extremely expensive. So the most popular approach is the based on the semi-empirical correlations. A lot of it is based on the linear stability method, popularly known as the E to the N approach. It has a lot of physics, so it's essentially like you take the mean flow, you apply some sinusoidal disturbances, and you use linear approximations to eliminate some of the nonlinear component of it, and then only solve for the linear part of it, of the disturbance evolution. And through that, we can capture a lot of the physics involved in the whole transition process. So but what it needs is a lot of non-local information. For example, if you're solving for a boundary layer or a flat plate, you would need to know the boundary layer thickness, and also also the pressure history as you build up. So you need to integrate through that point or across the boundary layer. So it's like a non-local operation. So in a modern CFD code, we are going to partition the domains, unstructured and stuff like that. So if you want to integrate the boundary layer thickness, momentum thickness, etc., then you have to get information from different processors. Makes it a little more convoluted and complicated to implement. Another important aspect here is like to be able to solve this problem, your grids used in your computations needs to be extremely fine in the boundary layer region. So unlike like in a typical engineering practice, be it RANs or things like that, we have some resolution in the boundary layer, but it's not extreme. Here we are talking in terms of say 60 to 100 points per boundary layer thickness, that type of resolution. So that you can capture the gradient, the curvature, all of that very accurately, and that's very important to be able to capture the transition process. And it's a very sequential process, so you'll do the flow first, and then do the stability analysis, and then look at certain things, and then feed back in, and it's like a very sequential process with a lot of manual intervention needed. It's not completely robust. It needs a lot of expertise like in transition physics, hydrodynamic stability, instability. So it's not very easy for a simple basic CFD engineer to quickly pick up these and apply this. And coupling with CFD brings its own challenges because traditionally stability analysis focuses a lot on structured solvers and things like that. Now we have unstructured solvers, many of them. So how we do the boundary layer discretization, things like that, it brings its own challenges. On the other hand, we have RANS-based transition models. This is a new paradigm that's being pursued right now. So this is very similar to a RANS-based turbulence models. So these are actually built on top of RANS-based turbulence models. So you have additional auxiliary equations, which tries to bring in some aspects of these problems, but it is a lot of it is based on like curve fits and empirical correlations. Not so much of the physics is. These equations don't have any physical representation. There are a few models which do come from the physics angle of it, but most of the popular models are more like correlation based. So it doesn't truly address the complex transition process, but for what it does, it does effectively is it's very cheap and uses local information. So for example, even if you need boundary layer thickness, it's not actually estimating the boundary layer. It's coming up with some kind of surrogates for those, which you can evaluate locally and still use it to identify things. And it's built on the existing RANS framework. So if as a solver developer, if you want to add these models, it's very easy because you're just doing the same thing which you did for your turbulence models. And more importantly, it's able to capture things on the global quantities of interest like drag and lift. If you look into the finer details, maybe it's not capturing the details, but the general trend in terms of how drag is evolving or lift is evolving, it does do a pretty good job. So in this chart, what I'm showing is like on the vertical axis, we have the ease of integrated CFD analysis, how easy is to put it in a traditional CFD workflow. On the right, we go how accurately it's capturing the physics. So the PDE-based, RANS-based approaches fall on one end of the curve of the chart, and the physics-based E to the N approaches are on one end. And both have their challenges, and we are trying to kind of bridge them and get them to a level where it's more user-friendly and feasible for a traditional CFD user to quickly use these tools to get where they want to go. So in terms of the physics-based methods, what we want to do is improve its robustness and ease of use, so that a non-expertise user can quickly use these tools without thinking, I mean, almost like using it like a black box. On the other end, we want to inject more physics into these transport-based PDE methods and improve them and help them get. So that way you have two different approaches which you could use to come at the same answer and use it like as a cross-validation also. So that's the goal of this whole project. So for achieving that, like the CFD tools I'm going to focus on, like what I've been using in my workflow, is the NASA Overflow CFD solver, which is an structured overset grid-based Navier-Stokes solver. My colleague, Nathaniel Hildebrand, he is pursuing the same path, but he's using the unstructured Fun3D solver to do the same things. So we are within the group, we are trying to implement this in two different solvers so that we can have a code-to-code verification and sort out some of the issues. And an equivalent effort is also being pursued for the Vulkan solver as well. So the Overflow is a traditional overset grid-based Navier-Stokes with like a lot of options for spatio-temporal discretization. It also has the following. I'll get into what transition models are there in these tools later. For the stability analysis, we are using the last track solver, 3D solver. It has both the LST, the linear stability theory, and PSE, the parabolic stability equation approach. And currently with last track, we now have the capability to work with both structured and unstructured grids through this new tool suite called the PyLastRack. It's a Python-based tool suite, which we use to kind of automate the process and bring simplicity to the whole stability analysis. So what the typical workflow is, if you're going the stability analysis approach, we would use Overflow or Fun3D with the SA model and impose transition at some downstream location where we think we can have a large laminar region. we would compute the mean flow, send it to last track, identify where the transition is going to be, then update where the turbulence model needs to be turned on again, and then keep iterating it, and then through that approach, get the answer. And along that, we also need some generation tools and stuff like that.
You mentioned Vulkan. Who's doing that work?
So Steve Woodruff is doing some part of it. And I think eventually, maybe Ethan Vogel would also get into it. I'm not sure. That's because he's putting the hypersonic models in there. So Steve was doing the low speed ones initially. So first, let's go on to the stability-based pattern.
Balaji.
Yeah.
So you describe, you just described some process of iteration between stability analysis, but okay.
We are going to get into that. Yeah.
Okay, but I saw that you're going to describe just
PD.
transition PD.
No, both. So I'm going to discuss both so that we kind of know where we can feed from each other.
Basically, both approaches.
I mean, because this gives us some ideas how we can improve that. So we are trying to blend in both. So that's why, I mean, I'll touch a little bit more on, very little on this and more on that maybe.
Okay.
But yeah,
Okay.
That way you get the general picture, I guess.
Okay.
So for the stability-based method, this is the rough workflow. Typically what you have is like, you have a general CFD input deck, right? You have the surface, and then you kind of also specify which surfaces you want to focus on, where we want to identify where there is transition happening. Say, be it the fuselage or the wing, or if you just want to focus on the wing, let's say we take this, identify the solid surfaces where that. And what I mean by we have to give it an initial intermittency function means essentially we are saying at which point we start the turbulence model. So in a typical sense, usually we always assume the turbulence flow starting straight from the leading edge or anywhere, right? But for doing the stability-based transition, we want a laminar-based flow. So the way to do that is you specify, you can do this with both SA model and SST model. So in what happens is typically we multiply the turbulence production terms with a factor, which will vary from 0 to 1. Turn off turbulent production where it's 0, and you turn on turbulent production where it's 1. That's one approach to do it. There's multiple ways to do that, but that's the typical approach which these solvers do it. So you try to delay transition, right? We don't have as much laminar region. So based on your prior experience, or like if you don't have any experience, just set it at the most, say 3/4 of the wing chord, if you think it can achieve laminar flow. Sometimes that might be too large because you might have an adverse pressure gradient, flow might separate if you try to achieve a laminar flow, but this iterative process will help you overcome that. So you can use some physical insight to set where your initial transition location is, or you can just randomly initially set it, and then the process is robust enough, it'll recover from that and fix it. So what we will do is we will set a rough location and then solve the basic CFDs, have the CFD solver run through your flow, converge it, and then write out the solution file into a neutral file format, which we send it to a solver independent module. So this can be coming from any solver of your choice. So the solver independent module will receive the grid and the flow data in a neutral format, identify the solid surfaces, build profiles, essentially wall normal velocity profiles, which the stability analysis tool would need, and then, write it out in a format that the stability analysis tool will be able to use and send those. And also, you have to find integration streamlines to do the analysis. So it'll build all of that. The file abstract tool comes in here, and then it will send it to this stability analysis tool. This can be either last track, which we are using currently, or some other stability analysis tool you have. You can also use a surrogate model to do the same thing, which is what one of our colleagues, Vishal, is trying to do. He's building these machine learning based tool, which would replace the stability analysis tool with that. Or you can have a data table lookup, which can do similar things. So some groups in Onera and DLR are doing that approach for that. So the stability analysis will get the tool and then kind of predict the growth disturbances and give you an N factor. And based on either the facility or prior experience, we can say that, oh, if the n factor, the exponent becomes to a level 8 or 9, that is when transition would happen. That comes from the calibration you do with the test facility or prior experiments. And then you would interpolate the computed onto the surface grid and then send the n factor distribution on the surface grid back to the neutral independent module. That will receive the n factor and think if the location of where that n factor was achieved had changed from the previous iteration. If it had changed significantly, then it thinks, oh, we need to iterate on this solution. So what it'll do is it'll say, oh, we have not yet met the convergence criteria. So it'll send back the n factor curve, but along with a new intermittency, the new intermittency being where the flow is going to switch from 0 to 1 in terms of turbulence production. And then send it back to the CFD solver. We again run through the CFD solver, converge it, get the mean flow again, and then go through the cycle. At some point, we know that where the location of transition being predicted is not changed. When that achieved, then we terminate the runs and we have the results. So that's the whole thing. And this is like currently done through, as you can see, the solver itself is either C, Fortran, overflows entirely Fortran. Last track is completely C++, and last track is like Python based script. And then we have on top of that additional bash script, which automates the whole process so that you give the inputs and then they say go, and then the entire process repeats for you automatically.
So for the stability analysis, how do you choose the wave numbers?
So that is what we have tried to make it kind of automatic in PyLasttrack so that the user like Chaulian and Fei and Milan and Pedro, through their vast years of experience, have kind of identified narrow parameters. So they have tried to make it so that I'm no stability expert. So to me, it should be a black box. So that's the goal of this whole project, is to make it as robust as possible. So through our own experiences, we've been kind of improving the process a little bit. It's not yet fully there yet, but we have tried to kind of remove most of the bottlenecks and make it as simple as possible.
So the intermittency function is defined on the surface, right?
Yeah.
So for any point in the volume, you base it on distance function.
Yeah.
And you do it like for every, not only within boundary layer, even if distance is very big, you still.
Yeah. So that's why that's one approach which we can still refine on.
Yeah.
Right now, because it's a surface intermittency based thing, right? So we are assuming that every wall normal point which can associate with that point in the volume uses the same intermittency. That may not be completely correct in a lot of cases, but unfortunately, the current CFD solvers are built to take in that particular parameter. But we do have the ability to actually go change that and give a more volume-based intermittency. But the stability analysis itself will only still be able to give you only based on a surface.
But also kind of beyond boundary layer, if distance is very big, so then why worry there? So that
yeah, so it may not affect it, but it might matter. For example, if you have a turbulent wake coming through,
Like you have a slack
wake coming through, then you would have to actually address that to say that, oh, this region should be turbulent.
But does this wake has relation to what
in some cases
they
do?
So that
Instigate a team to get to the bottom of this, and you're fast tracking the process. It'll take no more.
somebody's mic.
Sorry.
okay. Anyway,
Yeah, but you can have, that is the whole aspect of, I didn't probably talk about here. Receptivity is how much is the far field disturbance actually start going to affect into your flow. Things like that can, especially in turbo machinery and things like that, can have some impact.
For the stability analysis, do you just take the small boundary layer portion, or do you take the entire?
So what we try to give is we give, like in overflow, what we end up doing is we build a near body grid, which is say maybe 3 to 4 boundary layer thickness, and then we give that. But in Fun3D, we give the whole solution back to the stability.
All the way until
where we think it's free stream. Yeah. And I think when we write the profiles for stability analysis, it'll be able to identify where the edge of the boundary layer is and truncate it. So it will do that.
Is it guaranteed that the n factor distribution will converge eventually?
So
Or
yeah,
can it cycle, or?
we have some kind of under relaxation, eventually it does. but there are caveats, so I'll get into that. Yeah.
So conceptually, it's very easy for me to understand this on something like a cone at zero angle of attack. For more complex geometries, more complex shapes, do you end up having to feed the whole shape and geometry into last track? Say like a realistic wing swept at an angle.
Yeah, so
You end up having
the
to
way
feed
we
that
do
whole
that,
geometry into last track?
the whole geometry will go in, but it'll kind of be bifurcated into portions. Because right now, like say, if you have a streamline coming from the fuselage nose, like for example, if you have a fuselage nose and that's somehow coming back into the, say, the root of the wing, how to completely track that is not trivial. So
Yeah.
your ideal way is to kind of break it into surfaces, and each surface would be handled as a separate. And but like in those common regions, sometimes you'll have to give a separate section of that. But we do give the whole thing essentially.
And I imagine doing those eigenvector decompositions is then very difficult.
No, but I think the input to the stability solver is just one.
Just
line.
1D profiles kind of.
1D
Yeah.
lines.
Oh, so we're not doing any three-dimensional, we're just doing a local 1D problem.
Streamlines. We integrate through the streamlines. Well, Pedro does, we can also fold in the more planar marching techniques and things like that too.
Yeah, I was thinking of something like PSE, so.
So we are using essentially PSE. But you can use LSD, PSE for these. That's what we are primarily focusing on. So this is a classic example to guide you through what happens for the stability base. It's like, this is a classic Schuber-Cronstedt test case for a flat plate, natural transition, low disturbance environment where you have transition due to Tomian shifting waves. There's a whole range of experiments that was done in the 60s with different turbulence intensity levels. So the workflow is essentially, you start with the red curve. So as I said, the intermittency is where I say the turbulence SA model is going to start be turned on, and before that it's going to be turned on. So initially I set the transition at say roughly 3.5 million Reynolds number location. And then have that the flow converts, feed it to last track. Last track tells me the transition is based on how we do that is for each disturbance level, there's a correlation called max correlation, which will tie that to a particular n factor. You can use that to determine what n corresponds to transition, or for each facility, people have come up with certain n factors which you can use. So through that, it is going to tell me transition should actually happen at say 2 million or 2 point some million. We have an under relaxation parameter to make the process more robust and not noisy. So we won't directly update the solution with 2, but we would use an under relaxation to put it in the next iteration somewhere in between, and then iterate. And within 2-3 iterations, in many cases, we get the converged solution, and we get a good prediction of the transition behavior, like where transition onset happens, where transition ends, and so on. But there's a critical parameter here. The intermittency is like 0 and 1, but in actual physics, that it's going to be somewhere between 0 and 1. It's not a binary thing. So it's a real range through that. So there is something called intermittency distribution function, which kind of tells you how it evolves from 0 to 1 over what length. And that is important because that determines your transition zone length. As we all know, in some cases, the e to the n methods can only predict the transition onset. But from onset to where turbulence eventually happens, there can be a huge length. So if you miss that, you're going to predict something like if you quickly say 0 and 1, then it's going to predict it reaching the fully turbulent value here, whereas it actually reaches the fully turbulent much downstream. So there is something called intermittency function, which is one of the key parameters in doing this. So what it does is, as I said, instead of if you use a 0 and 1 binary type approach, it causes a lot of numerical convergence difficulties with these range-based solvers. So it's nice to have a smooth function which will ramp up the turbulence prediction from 0 to 1 over a length. But that length is kind of unknown. So typically what we tend to use is there's this classical Narasimha's intermittency function, which he designed based on some experiments, except there is a transition length, zone length, which is an unknown. We have the estimate for the flat plate, but if you were to apply to this whole range of problems, we don't know that length. And that can have a significant impact. If you have like a separation bubble zone, then the transition happens immediately, very quickly. So usually you don't have too much of a length, so there the length doesn't matter. But if you have a long bubble or like you have a range over where the pressure gradients are kicking in, then you might end up with a long layer. So this is one of the problems which we've been trying to address, and like we are within our group, we are doing it. So for TS waves, one simple thing is, determine that you give a length based on the n factor itself. We know that, at n critical, whatever n critical, be it 8 or 7 or 9, we know that transition onset is going to happen. So you can say I'm going to roughly give a number between 0.8 to 1.2, that length of region to be kind of the transition zone length. Of course, it has no physics. You have to kind of use some experiments to pre-calibrate this and determine that. So you'll have to change that length for different configurations. So it's not predictive in that sense. But the more correct approach is there are some groups, say within DLR or ONERA, where they have some other correlations. Some groups are essentially saying my transition zone length is 2 grid cell units. They don't care about actually getting the transition zone length right. They just want to get the transition location right, and they don't care about the length. But if you want to care about the length, then there are other correlations which kind of says, if you have a flat plate, then use this correlation for the length. If you have a short bubble, use this. If you have a long bubble, use this. But then that becomes more manual intervention. So what we are trying to do is come up with a more generalizable n factor distribution, which will be based on your RE theta critical and your pressure gradient parameters, because usually those two tend to kind of determine the transition zone length. So our group has been working on that. So the first one is the simpler one, which we tried doing. So this is like, changing the length based on 0.8 to 1.1 n crit kind of thing. So this is again the Schubert and Skramstad flat plate. So the dashed line is the intermittency going from 0 to 1. So as you can see, if we increase the transition zone length in the blue curve, then you have a different curve with a slightly different slope, right? Gradient. Whereas if you reduce the transition zone length, which is the red, then you quickly become intermittency reaches value 1 here. And based on that, where your CF changes also changes. So this is like the range of experiments from the Schubert and Skramstad experiment. So where they have kind of where is the initial transition onset and where is the fully turbulent region. So the symbols, the green dots are actually that. So based on how you set this, you can kind of capture the trend. Whereas if you didn't have a clean enough intermittency function and it was very narrow, then you will probably many times you may either get everything to collapse here. You'll get a 0 length transition zone, or you may not get this right. And getting this zone length right is important, especially for hypersonic flows and things like that. So this is just one very simple approach, but this is not a very robust approach. So we are currently exploring another approach, which is based on a pressure gradient and RE theta.
Why do you remember why by 6 to 8 million the CF is not exactly the same for red and blue?
Like here, it's still changing because the virtual origin of your turbulent region shifts slightly. So you'll have to go further down before they actually come close together.
Yeah, I remember now.
Yeah, we looked at it quite a bit that time. Yeah. So that is one thing. And this particular is for natural transition. Now we add crossflow. Nobody has ever looked at intermittency for crossflow. And then on top of that, you add a scenario where both TS and crossflow are sitting on top of each other or interacting with each other. We don't have an intermittency function for that or how it should be. We don't have any experimental data on that. So those are the things we are currently investigating. And we are having a modern experiment that's being designed and going to be probably run sometime later this year or next year, and hoping that that experiment gives us more data to kind of fine tune these aspects. So this is a typical case. This is the NASA juncture flow, not that the original juncture flow, but this is a juncture flow with the symmetric wing. It's a NACA 0012 symmetric wing. Actually, it becomes NACA 0012 at the break. At the root, it's still a NACA 0015, and it's blending over through that. So this experiment was done to actually focus on QCR corrections and things like that for turbulent flow in mind. But as a piggyback, they also did a transition experiment on that initially. not as detailed, but we got some good data on that. So we have some transition data on that. So this is the classic example. So I'm just showing some pressure contours for different range. And like we had reported the results for this in one of the papers. So this is the stability analysis results. So how we go about doing this is, since this has both TS and crossflow, how do you determine where the N factor actually is, which N factor is critical is like not one number. It has to be a combination of TS and crossflow critical number. So what we do is we use something called this dual N factor criterion, which is detailed in this paper. So it kind of tracks the interaction between both TS and crossflow. How, if you have, say, a TS of 4, but you have a crossflow factor of 4, these two together can mean something larger than what they are. So what we end up doing is, this is more like a not completely predictive. So first you have an experiment where you have the data. So we do the stability analysis, and then say for 2 particular angles of attack, we take the data. Say the black line is essentially the transition prediction from the experiment. We get the N factor values on that, plot it on a curve, and try to fit a curve fit through that, and try to fine tune the coefficients. So we have some kind of a N factor curve, dual N factor curve that kind of tracks that. Use that to kind of then use it to predict other cases and see how it does. So we tuned it based on 2 particular angles of attack, 0 degree, where we know it's completely TS dominant. So that's why the blue is, the N factors are all here. It's very, very small crossflow N factors, are all almost TS dominated. And angle -4 degrees, where you have a bit of both crossflow and TS. So that is the pink or magenta symbols. We fit a curve, and then here I'm showing essentially the blue, where the flow becomes red in these contours is where the transition is predicted based on this approach. So as you can see, for 2.5 degrees, where in this case, most of it is TS dominated with some crossflow in the inboard section of the plane. Again, the method is able to capture that quite well. And -6 degrees, where it's completely crossflow dominated, based on how you can see the kind of noisy front coming from the experiment. You can kind of see that, and our method is able to kind of capture that. Of course, this is not completely prediction, because we had to kind of fine tune it. So it has to be this approach has to be recalibrated over each facility and flow configuration, and you have to kind of tune it. So that is the drawback of this. But provided we have enough data, at some point, we are hoping that this approach becomes more robust, that without much of tuning, you'll still be able to get a reasonable enough result for a whole set of similar configurations. And we apply the same thing to the CRM NLF, which is a transonic wing designed to mitigate have as much laminar flow as possible. The wing was designed to attenuate crossflow disturbances and also TS disturbances. So this is again through the iterative process. So since this case was a transonic case, you have actually a double shock system sitting on top of the wing. There's one shock system which cuts through here, and then another one in the outboard, slightly shifted from that. And what happens is, in the inboard portion of the wing, you have much earlier transition, which is predicted by the. So here it's what I'm doing is actually the TSP image superimposed with all the predictions from the stability integrated analysis. So where the flow becomes from gray to darker gray is where the transition is supposed to be. So the experimentalists actually drew this orange line, which was supposed to track that, but this was not done in a very robust way. So it's kind of hand wavy in that sense. And the green or the blue curves is what we predict through the iterative analysis. So through the iterative analysis, what we did see is, as we go outboard, the transition is entirely shock limited. In the inboard, it's a lot of TS. There is some cross flow near the break, but the approach is able to kind of converge quickly and capture the general trend very well for across different conditions. And the coefficients were not, at least the coefficients were not too different from the juncture flow model as well. The critical N factors are slightly different based on the roughness levels and the disturbance level, different tunnel, etc. So that's a good successful case we are able to do. Moving on to PDE-based methods. As I had mentioned, PDE-based methods are relying on correlations and local surrogates for things like pressure gradient or boundary layer thickness. And a lot of it is anchored to a very limited data set because it's correlation based. The initial ideas came all from a kind of bypass transition domain, a lot of low speed, high turbulence intensity kind of data with very specific pressure gradients. So the correlations essentially came from a very narrow set of experiments. So they are not very general in any sense. However, they've been super popular and they've been quite good. So people have quickly adapted that. And what they end up doing is they cast what is important for transition prediction, some of these parameters in terms of PDEs, and through that identify the same intermittency factor, which is going to say how much, when I'm going to turn on the turbulence production in the turbulence terms equations. It's still the same gamma, but each method goes about in a slightly different way. The most popular model is the Landry-Mentor model. So the original model was proposed in 2009. So what they end up using is two things. One is they use the scaled vorticity Reynolds number as a surrogate to estimate RE theta, because you don't have the theta. And the scaled vorticity Reynolds number actually goes like this. It reaches a maximum value somewhere in the middle of the boundary layer and then goes back. And they found that for Blasius flow, that REV maximum location versus if you divide it by the actual RE theta, you get like a 2.193 ratio and things like that. So based on that, they kind of say that, okay, we can use this parameter as an estimate for RE theta. Of course, it's not correct if you estimate it here, or here. It's only correct at one location, but that's enough because usually that's where the transition onset usually happens. So if along a wall-normal point, if the vorticity Reynolds number reaches a certain value beyond the critical RE theta, then you know the transition is going to happen and trigger on transition. Similarly, pressure gradient is established, computed through a different surrogate. So that way you're not doing any across the partition divide to get some data and things like that. Everything is kept local. So they saw two equations. One is for RE theta t. This is essentially to give for each location what is the critical Reynolds number at which transition would happen. And that is dependent on your disturbance level and pressure gradient. So they have a correlation which will tie that to that. So from the free stream, based on the disturbance level and the pressure gradient, you would kind of feed that. That information will, through this transport equation, will diffuse into the boundary layer. And within the boundary layer at each point, then you will have the critical Reynolds number at which transition is supposed to happen. Once that information is there, that information is then used in this intermittency equation, which is active in the boundary layer. And you'll say, oh, my current estimate for boundary layer momentum thickness is more than the critical number. So I'm going to turn on intermittency, increase the production, and then turn on the turbulence term. So you'll increase the gamma value. And this gamma is like the same intermittency function which we are using in the stability analysis, but slightly different meanings. So this will essentially go multiply with your production term of your turbulence term, and then essentially turn on the turbulence production in your RANS equations. So the LM model is tied to the SST equations. So the gamma would get multiplied to both the production term, it'll get multiplied to the production term in the K equation. So you can kind of, that's what I put there. So that's the way it does this. It's completely empirical. The transition zone length is empirical. Everything is based on some, it has idea of physics, but it doesn't truly capture the physics, because I said the intermittency is like intermittency because in actual sense, intermittency is like how much fraction of a time your flow is being spent as in a laminar state versus turbulent state. In the RANS form, everything is time average. So what is intermittency? Time sensitive quantities. It has no meaning to that. Here, it's just like a way to quickly turn on production terms and turn it off. That's all. But they've given it the same term as intermittency and the same symbol. So that's the thing. So this can only do TS, bypass, and separation bubble based scenario. Then somebody in 2015, they came up with the cross flow correction addressing to based on a roughness value. What they end up doing is, if you have roughness, then they will reduce the critical Reynolds number by a factor. And that is all calibrated based on one experiment done in the 70s, 80s. It's an NLF experiment done in ASU tunnel. So all of that is based on that one particular experiment. And this model has been quite popular. And then DLR came up with another extension. It's again a cross-flow model, but this model does not account for surface roughness at all. But it's also kind of predicts cross-flow in a lot of scenarios. So there are a lot of, this has the physics, it's very weakly calibrated. This has none of the physics, but still is quite successful. So you pick and choose. Then there is Mentor's stripped down version of the Langter original model, which is now called the gamma model, where he threw away one of the equation and folded it back into just have one equation and made it more Galilean invariant. The previous model was not Galilean invariant, so he tried to address that. But the crossflow is a work in progress for that. We have been looking at that, and we have that also. And the other popular model is Jim Coder's AFT model. This comes from the X-foil approach. It is coming from Drella and Giles' work, where based on stability analysis, we have these n-factor curves. Based on that, they kind of approximate those n-factors curve by some kind of a table, and you can all come up with a correlation. So this equation actually solves an n-factor transport equation along with an intermittency equation again. This model originally was coupled with SA model, but you can also tie it with SST model. All of these models you can kind of swap, which is the baseline turbulence model with some recalibration. This again handles TS and separation bubbles quite well. So this is another popular model which is quite out there. So within the different two mainstream NASA codes, we have most of these models implemented in some sense. We also have like variants, like for example, an SA-based LM versus SST-based AFT, which is not yet there, but like we kind of try to address that as well. And I would like to also point out there are some new hypersonic-based models also which are being put in, but they are not yet production ready, so they may not be there as part of the main release. So what are the problems with these PDE-based methods? There have been several workshops in the last few years focusing on just these PDE-based methods. There was a NATO workshop, AAA workshop. So this is a simple case. This is one airfoil case with transition. This is another airfoil case with transition. All the participants produce these results on the same set of grids, and we have a huge scatter. We cannot even come up to any agreement. This is reminiscent of the early drag prediction workshop and turbulence models and things like that. So why was such a big scatter? Sometimes they're supposed to even like the model has been specified, the grid has been specified, still we got a huge scatter in results. Why is that? There are two reasons. One was the grid itself was not completely, the grids that was provided was not sufficient for each of the solvers to kind of converge. Maybe they needed additional levels of grids to converge. Another thing was inconsistency in how the turbulence model, this transition model itself was implemented. For example, the LM model is supposed to be implemented on the 2003 version of the SST model. A lot of people, because for whatever reasons, oversaw that. They implemented it on the 94 version. So the calibration is slightly off. So they ended up with a slightly different result. Or sometimes they have these limiters inherently turned on in their solvers, which shouldn't have been turned on when you're using these transition models. So that would give you a different answer. So there was a lot of inconsistencies, and that has been through the turbulence.
What about iterative convergence?
So iterative convergence, a lot of people try to get there. Again, this is again a very tricky point, because what happens is in these solvers, like if you see the iterative convergence, say for the turbulence part of the RANS equations, you will get a good deep convergence. But if you see the transitional equation, sometimes you don't get deep convergence.
And you look only on what? On convergence of turbulent solution, or you look at residuals?
So we look at residuals, but like again, the kind of quantity which you would use to determine that this is converged is tricky. So in some simpler cases like the airfoil, subsonic flows, most of the times you can get to 8 orders drop in residual for both equations. For some of them, you don't get that. If you have shocks, you might stall at like 3 orders of this thing. So there's a lot of confusion on that, and that's I'll get to that aspect as well. So our group has been trying to at least resolve one aspect of it within our group. So between Fun3D and Overflow, we have been trying to look at the implementation aspects of it closely. And we kind of did a variety of cases and kind of said that, oh, we can get convergence on these quantities, both codes get to the same level, figured out where the inconsistencies were in the implementations, removed that. And as part of that, we developed a set of grid solutions, which we are going to put in terms of in the turbulence model website as guidelines for others to implement things. And one of the things we found from that work is that if you look at global quantities, it's very easy to establish that like two solvers are going to the same answer. But if you look at point quantities, say like skin friction at a location in the transition zone, then it becomes very difficult. Say overflow was getting there very quickly, but Fun3D was like had still not got to the converged level. So what metric to use for these transitional flows besides the global quantities to kind of say that, oh, we are there, the results are converged, or your code has been implemented correctly, those kind of things is an open question. And we are doing similar thing for AFT and the gamma transition model as well. And another thing we did realize in these transition model, unlike turbulent flows, say for a typical turbulent RAN solver, the guideline is y plus 1, which if you're hypersonics, then you go to y plus 0.1, and some guidelines on the growth rate, which is good. Here, unfortunately, for transition models, you need at least a y plus of 0.5 and a growth rate of within less than 1.1 within the boundary layer. And your streamwise spacing has to change as you get close to if you are like in the transition zone. So it's a lot more stringent. So the grids to get converged or reasonably converged results is quite large. So in this case, for an airfoil, having 2000 points and stuff like that is quite large. And whether that is like feasible for a practicing CFD engineer, that's one of the questions which we're trying to address through mesh adaptation, because we need large grids. Can you somehow reduce the grids, and without you having prior knowledge, can you somehow make the solver insensitive to that and get you the right result? So there are two approaches. Nate is trying to go through the adjoint-based adaptation as well as metric-based adaptation, unstructured adaptation in Fun3D route. In overflow, we are going through the Cartesian AMR type adaptation, but more like solution-based adaptation rather than an adjoint, because we don't have that capability. Jim Coder's group students, along with Marshall Gilbreth at MIT, he's also going through an adjoint-based method. But the key thing with adjoint-based method and transition models is these transition models have a lot of correlations. So there are a lot of if-then conditions with a lot of jumps. They are not smooth. So you'll have to smooth those correlations to be able to do adjoint. And additional, like these transport equations are much more stiffer. So that to get a good converged baseline solution is very hard in these. So they are now trying to modify the transition equations and these correlations so that it's adjoint friendly, and then trying to go through that, which means you'll have to go through another sequence of recalibration of these transition models and things like that. So there is some. So as a quick solution, we are going through solution-based adaptation. We are using something like an undivided vorticity as a metric, and we are getting some reasonable results. We presented some of that in the ICCFD conference, and it's going to come over, like we are working on a computers and fluids paper on that. The limitation with the overflow approach is it's like an isotropic adaptation. So unfortunately, even if you only need adaptation in the wall normal direction, the overset capability is going to add adaptation in the streamwise direction also. So you may not get as much savings as what you would get in the Fun3D type approach. So that we are trying to also sort out and figure out a way. So this is, again, going back to the CRM NLF, I'm showing the same thing run with these two popular transition models, the AFT and the crossflow based LM model. The blue dash or the cyan dash line is the predicted transition front from the experiment. And these two transition models is predicting a much smaller laminar region across the conditions investigated. So which means they are not doing very well for this transonic case. Why? Because these models were calibrated on low speed flows. So they didn't take into account the compressibility effect in transition. So for transition, compressibility adds a stabilizing aspect up to certain Mach number. Beyond a certain Mach number, again, things change and goes differently. But in the transonic range, it's supposed to help stabilize the boundary layer and enhance stability. Because these models didn't do that, they are not capturing it. So they're predicting a much earlier transition than what it's supposed to. So they're quite flawed. So to address that, we are using the stability data to kind of know that how much is the stabilizing effect and trying to correct some of these correlations to add the Mach number effect onto that. So for a flat plate, the original correlation would predict transition to be along this green curve, pretty much flat. It then does not vary based on the Mach number at all. RE theta is always fixed. Whereas from stability analysis, we know it should increase. So based on that, we add a Mach number correction to these correlations to help you bring back that missing piece of physics into the solver. So through that, we had recalibrated. And what is good about that approach we are doing is we are still trying to keep it such that it doesn't break the original calibration. So when you go to low Mach number or bypass error, we would still have it. But there are other groups across the world doing a similar effort, but they are either solving additional equations or modifying the correlation such that it no longer works for the problems which the original model was calibrated for. So different approaches, you pick and choose what you want. But again, currently our approach only takes into account Mach number. But another important thing is, say, for example, your Mach number increase, but you have an adverse pressure gradient, then that kind of cancels out the stabilizing effect. So you would not have to have the correction. So you'll also have to fold in the pressure gradient parameter, and which is what we are currently working on. And so this is one result where we are showing without the pressure gradient effect, but just with the Mach number, you can already see that from this blue line, now it jumps up closer to what should be the actual line.
Actually, there it could be better than when it looks, because when we spoke with experimentalists, that
this line here is like
might not be the
questionable. It should be much like if you plot it against stability analysis, then they are much more closely comparable. So this is one aspect, and there is a similar aspect to it in the AFT model as well. This is again the juncture flow where we did the dual N factor calibration and we got good results. So here, this is 2009 model, which has no cross flow. It can only model TS. So blue is laminar, red is turbulent. So you can see that it's predicting a much more larger laminar region, not capturing the measured front. The roughness-based crossflow model is again not doing very well. It is it's capturing somewhat some regions, but again, we are just like reading into the results. We did do a sensitivity of the roughness levels. We had to use extremely large level of roughness to get what we want. On the other hand, the DLR-based crossflow model didn't account for roughness at all. But somehow in this case, it got the result spot on. Across different angles of attack, we tried and everything. Because one possible reason could be that they had calibrated their model on a similar configuration in their group. So we are currently, as part of the modern experiment, we are planning to study a sensitivity to the roughness levels. That way, we would kind of see how this model does that. Also, we can then improve the 2015 model, which was relying on that one particular data set with some additional data sets. And then also use that experiment to kind of identify where TS and crossflow are interacting and then adjust the thing. So all those aspects can be addressed through that new experiment. So this is again showing that across conditions, the DLR's model is actually doing very well. So the final missing piece in these problematic area in the transition prediction models is this. As I said, free stream turbulence intensity is very important. But in the experiment, you usually measure it at maybe the inflow location station and maybe near the leading edge of the particle. And sometimes we have the decaying trend. You know that it's going to decay a little bit as you approach. And in the CFD sense, say if you're solving SST, then you know that the K equation is going to decay. So what value do you specify at the inflow so that you can capture the decay is one aspect. Also, if depending on how much is your inflow domain, if your grid is not adequate, you're going to dissipate that away. So you may not get the right turbulence disturbance level there. So what people do is two different approaches. They know what value you need at the, say, 0 is, say, the test location. You know what value you need. So what they end up doing in the SST-based sense is they adjust both the eddy viscosity and the K value to some very high values and tweak it such that they can get the same value that they want at the leading edge. except that there are multiple pathways to get that particular value, and each can mean completely different thing. So for example, this is a bypass transition case. So, there are different ways which you can, the symbols are the transition from the experiment, the decay, they had measured that. There are multiple ways we can approach that. And depending on what values you do, you can get a different answer, even though they are all matching the decay rate quite well. So there is a problem in that, like how you do that. And this information is not available in the experiment. So you have to be very careful in how you do that. And alternative approaches, and sometimes if you're for certain levels of disturbances, no matter how you adjust it, you'll never be able to get that value. For example, the CRM-NLF case, depending on the domain size and that, whatever you do, you could never get that. So you would have to do some other way of enforcing the disturbance level. The other approaches through Spalater and Rumsey, what they said is like they added a source term which will essentially freeze the decay in the upstream region. As you get closer to this thing, then that would kind of mitigate that effect. So you'll get the same value, except that this was designed with fully turbulent cases in mind. So what was happening is for these transitional cases, this additional source term was actually affecting the boundary layer behavior in the laminar region. And say, for example, the CRM-NLF case, if you use that particular approach, we were getting the wrong pressure distribution because those source terms were interfering within the boundary layer. So you have to kind of do some shielding of these additional source terms to kind of make sure that like the boundary layer is not touched, but still can capture the right disturbance level. So that is one such area we are currently looking at, and this aspect will be presented in the aviation 2025 paper. The final big elephant in the room is this convergence of transition models. There's no clear answer to this because each transition model behaves very differently and they achieve different convergence levels. Sometimes they give you a false sense of converged behavior. Everything flatlines, but then you change a little bit and slightly perturb it, then you get a second level of convergence. So you're never thoroughly sure that you're converged. So different groups are approaching it in different way. Pseudo transient continuation is one approach. Some people are changing the PDEs itself to make it more well-behaved. So this is an ongoing topic of research. Nobody within our group is currently pursuing this. Unfortunately, I put forth this question to Hiro to look at it. So at some point, maybe we'll start looking at it. So yeah. So our group is pursuing these dual strategy to kind of feedback with each other to get to improve our capability to predict transition and then make it more automatic so that everybody can use it for practical scenarios. We have kind of improved the robustness and ease of use of stability-based methods. Still a lot more work remains to be done, especially how you specify intermittency, specifying N factor, etc. In terms of PDE-based methods, we are trying to inject more physics into the approach, ongoing effort, and there are several areas which we are currently looking at, and in coherence with some experimentalists so that we can have some feedback into that. Thank you. It took a long time.
Yeah, but this room is still available, so question.
So with the non-PDE based transport methods, you were worried about the transitional length. With the PDE ones, it's just sort of, you get it, whatever it does, is that right?
It has a transition zone length, but again, that is very limited correlations. So we can feed the same thing back into that. So, but beyond that,
you're that worried about that at this point, because
there are several pieces there.
There's a lot of
there's a lot more pieces there which is worried about that.
Yeah.
From the transition onset itself is problematic for that. Although, like if you were using it within the regimes where it was kind of calibrated, you do get quite good results.
So how does the total cost compare to a fully turbulent simulation?
So compared to a fully turbulent computation, say if you take a PDE-based method, right? Because you're solving depending on which transition model you pick. Most of these, except for the gamma, everything is additional 2 equations.
Yeah.
So you have to add into the cost.
20% cost.
20% cost to that. Or maybe no, but then the problem is these equations don't converge so quickly.
Right.
So a typical fully turbulent case, say for some of these cases on the same grid would converge, say within 10,000 iterations, 20,000 iterations. Here I would need minimum 100,000. So like a 5x sometimes on that, depending on the problem.
You have to repeat, right?
No, for the PDE-based method, it's not repeating, but for the stability-based method, it's essentially reverse, right?
Yeah.
It's usually maybe 3x because you're doing 3 times the iterative, but like, the turbulence cost itself is quite small. A lot of the cost comes from solving the stability analysis, not so much solving the stability analysis, especially for like building the pieces. For 3D cases, building the profiles. For a structured grid, it's cheaper. For unstructured, to extract the boundary layer profiles and everything is little more expensive. So that is one of the pieces which has been like looked into.
But the convergence issue, I'm guessing, is there for the stability-based one also.
Not so much, because there it's predominantly relying on the turbulence model, right?
Oh.
So it's like
Because
as long as the intermittency is kind of smooth, if it's not point-based, it doesn't affect the convergence as much.
There's a question from online. Speak up.
Hi, Balaji. Can you hear me?
Yeah, we can hear you.
Yeah, we can hear you.
Yeah, thank you for the great presentation. I have a question about the message resolution requirement. Could you comment on the message resolution requirement of the stability-based method compared to the transport-based transition models?
Yeah. So for stability-based methods that I had mentioned at the initial, you at least need 60 to 70 points within one boundary layer thickness.
Mm-hmm.
So that is the requirement.
Mm-hmm.
Whereas for PDE-based methods, the current guidelines we have kind of identified within our group for subsonic flows is Y plus of 0.5
Mm-hmm.
and smaller. And
Mm-hmm.
also for airfoils, you would have to make sure that you have adequate resolution in the leading edge and trailing edge regions.
Mm-hmm.
And then if you're having separation bubble-based transmission scenarios, you would want to have at least like 3 to 4 points within the bubble.
Mm-hmm.
That kind of helps.
Okay.
Although I think depending on the TS-based scenario, say for a separation bubble, the stream-based resolution is a lot more important than wall normal resolution, whereas a TS-based transition stream-based resolution is equally important. So that kind of changes.
Okay.
So that is the current identification we have within the group. Yeah.
Mm-hmm. Yeah, thank you.
And
I
a
was
growth
curious.
rate of 1.08 kindish within the boundary layer for even for PD based methods.
1.05.
08 or 05, yeah.
Okay, yeah.
Gradual, not abrupt. But that could be debated. I think Mentor has a guidelines as part of ANSYS where he says you can use up to 1.1. So through the automatic adaptation, we are hoping to get answers to some of that, because maybe close to the wall, you don't need Y plus 0.5 as long as you capture the vorticity maximum. If you capture that profile, maybe that is adequate. But that, because currently we are exploring through uniform adaptation and things like that, that has not been explored. But that is one question we are trying to look at. And maybe that can refine the guidelines a little more.
Yeah, thank you.
Thanks.
I was going to say that's an argument that people like Mike Park always make, is that the initial laminar region isn't super.
The viscous sublayer is kind of not so important, and
the grid resolution there isn't as important as grid resolution immediately above that.
Yeah. But these guys will argue differently. The stability guys methods will argue slightly different.
Yeah, I haven't seen that. I've seen that that initial part is important for the profile. If you compare, I've been doing with refine and all of that, you compare with more points there, then your profile changes.
So are you decoupling the resolution in, say, the buffer layer and the viscous sublayer then? And you're finding those two independently?
Yeah.
Okay. Interesting.
Adding the prismatic layer for the initial part and having different resolutions near the wall, it changes the profile for stability.
Because I think we saw this with on 3D's metric-based adaptation as well. Like when Nate was doing it, it was adding a lot of grid in that region, but didn't help us in terms of stability. So there is some sweet spot where, like, of course, it's not maybe as important near the wall. But where in that region within the boundary layer we are going to add that can vary.
Yeah, he added that join, and then that join was putting more points below.
Okay, that's interesting.
Yeah. So that's
I'll have to follow up with you on that. So I had a question.
Yeah.
So one of the things we worry about is the peak heating or the peak skin friction. And one of the problems with transition is you get this initial overshoot. So from what I've seen both in your past work and in this presentation, a lot of times it's kind of a smooth ramping and you don't get that kind of overshoot that happens.
Yeah.
So can you talk a little bit about that and
So
your efforts to address
that's
that?
more important for hypersonics. And like Ethan Vogel has within the group is looking at that. I think he had a presentation not too long ago.
Last presented at SciTech.
SciTech, and he's been working on that especially to kind of pick that transition. In the past, people they've done is they've approached it in a different way. One way is like I think Arnal had predicted, like in transition, like instead of limiting it to being 1, you temporarily allow intermittency to go beyond 1. So that way you would get the peak, but that you couldn't anchor it to any particular experiment, and you would have to kind of tweak it. He had some analysis for that, but it's not very robust. So now Ethan, what he's trying to do is based on different data sets, he's trying to assemble he's trying to fit essentially the same function through that, but he's optimizing some additional coefficients so that you would get that peak. So that, because that's very important, yeah. But currently the length is 1, the peak is another one, but like in subsonic, the peak is not so much as being, we don't have much data in that sense for that.
I think most of the people use the experiment by Tom
Howard's experiment.
Horvath.
Yeah.
Yeah, the
The
tunnel experiments, a lot of it. Yeah.
So there's a lot of papers from China using those experiments to calibrate the models.
So he is trying to optimize the transition zone length and possibly get the peak as well. So yeah, he's looking at that.
Yeah, I mean, that's a constant plague for us is
Yeah.
people always want to know what the peak heating is, and the peak heating occurs right there.
Right there. I mean, people have, that's an interesting, I've spoken to Pedro about it as well. Like, I think that's an interesting thing. Like, I think Arnal, or one of them, they had kind of said that the peak value is essentially, say, for example, if you, this is the fully turbulent CF value or CH value, assuming it'll look the same thing, the heat transfer would look the same. They kind of said that you continue this to where the transition onset is. And that is the value at which would be the peak value you would probably hit, and they try to get that folded back in. But I'm not an expert in that to kind of make whether it's right or wrong. But they said that is about the maximum value to hit.
I mean, you're in front of the podium, you're more an expert than I am.
You're all experts, I guess. Yes.
So do you foresee wall function based methods for this PD, partly subsonic transonic?
I think there are some efforts on that. Like people have tied it with, say, DES. Again, it brings its own set of problems. The DES shielding interferes with the PDE's shielding already inherent in these transition models. So that's one area. And then
DES, I'm saying wall function.
Even wall functions, yeah, you can use that, but like how much you can, because you still have to get the vorticity maximum for some of these. So your wall function, what Y plus you allow for that is kind of tricky. So there are like in wall functions, wall model, also like DES, that approach, everything is being also looked at.
No more questions? Almost 12:30. You have very good discussion. But let's end it here, and then let's thank the speaker again.